So thank you for coming to the talk. So I'm going to talk about diffusion curves today, with a focus on whether they're a good fit for SVG. So I'll talk about what they are, and we'll look at some of the key research papers and their features kind of from the point of view of an artist or an author. And then we'll look at some of the challenges to including them in the SVG standard. So I've got lots of references. So if anyone's interested in reading more about what diffusion curves are, this is a good place to start. And I'm sure you can get the slides from somewhere, or you can ask me for them. So I'll introduce myself. So my name's Nikos, and I'm a software engineer for CISRA. So CISRA is a Canon research company which is located in Sydney. And one of our research areas is diffusion curves. So a teammate of mine, Peter Ilbery, is going to be presenting a paper at SIGGRAPH in November. And Cyril, who's down there, is one of the co-authors of this paper. So direct all questions to him. So I haven't been actively involved in the research myself, but I am lucky enough to have been able to watch the progress and to learn about the technology. And I've spent quite a lot of time authoring diffusion curve images. So one of my roles at CISRA is to represent Canon on the SVG working group. So obviously I'm going to talk about SVG and diffusion curves, and I think they're a good fit. So after this talk, you might agree with me. So what are diffusion curves? Well, so in their most basic form, they're a curve which is placed in an image plane. So they have a color assigned, and that color diffuses outwards to paint the space around the curve. So the colors on each side can be specified independently, and the color can vary along the sides. So in the example here, we've got orange on the left-hand side and a transition from blue to green on the right. So you can place many curves into the space, and they all interact together to form some sort of image. So here's an example. So I'm a programmer and not an artist, so don't judge too harshly. But the image took me about a day to create, and that's with fairly clunky tools. You could easily cut that time in half. But so you can see that you can use diffusion curves to create an entire image. And the beauty of the representation is that you only need to define the image features. So it's very much like traditional drawing, where you sketch outlines and then paint in the colors. So you could also create something more abstract, and that might be useful as a fill, sort of on a traditional vector object. So in my first example, we had just one single curve, so we saw that curves don't need to be closed. But if they are, then typically the color does not diffuse outside of the closed region. So the basic diffusion curve is a barrier, and it partitions the space on each side of it into two separate areas. But there have been many extensions to the diffusion curves model, and so we'll cover those through the presentation. So diffusion curves are a great tool for authoring images and gradients, but there are some other nice features that make them really appealing. So their definition is a vector format, so they're resolution independent. And so they address one of the major limitations of vector graphics, and that is creating naturalistic fills. So another aspect of this is that they provide a nice target for the vectorization of natural images, so converting photos and such to resolution-independent formats. So the representation is feature-based, and so that provides you with an intuitive drawing model, and it makes animation really easy as well. And also the representation is very compact, so that's good for transmission, and it should allow for an elegant SVG definition. So maybe you can sort of see why I think that SVG and diffusion curves are such a good fit. But before I start talking about diffusion curves properly, there's another member of the advanced gradient family that I want to mention, so that's the mesh-based gradient. So a mesh-based gradient is defined by some sort of mesh structure that has color controls at each vertex. So the color gradient for each patch is defined by those colors. And so it can result in similar image output to diffusion curves. And there are various mesh structures used. So you've got triangle meshes, which are very simple, but they're not very good for authoring. And so then you end up with some higher order representations that kind of make the authoring process more pleasant. But for all those cases there, each patch is individual and it's separated from the others. But there's another type called a gradient mesh as opposed to a mesh-based gradient. And so that's what's supported in Adobe Illustrator and Corel Draw. And so they do offer smooth transitions across boundaries. but unfortunately the algorithms haven't been disclosed. But there is a paper which was published by a guy called Sun in 2007 called Image Vectorization Using Optimized Gradient Meshes, and that describes an implementation that is very close. So mesh-based gradients are a long way ahead of diffusion curves because they're already out and they're available for use now, and people are doing some cool stuff with them. But they can result in a very complex mesh. But the good news is that they're coming to SVG 2. So SVG 2 is going to support Coons patch mesh gradients. So that's similar to what is in Cairo and in the PDF format. So a Coons patch is a surface that's defined by 4 boundary curves, typically Beziers. So the mesh is made up of a 2D array of these patches, and to calculate the color for each patch, you simply render a rectangular texture, and then you map that onto the patch. So the patch is a control surface, though, rather than a painting geometry. So the area can be painted outside of the patch if the boundary curves fold back upon themselves. So it's best to think of them as kind of a two-sided surface. So edges are shared between patches in the array. So in the example here, I've got a 2x2 patch. The top left patch is defined by 4 curves, while the others are defined by either 3 or 2, depending on their location. So the Coons patch format in SVG gives you a lot of flexibility in defining your mesh structure. So degenerate patches can be specified, that is with straight edges or zero length edges. So that means you can generate a triangle mesh if you want. And it also makes it easy to simulate some of the simple gradient types. So mesh gradients are an awesome thing to have in SVG in terms of lifting the quality of the images that you can create. But there are some issues, and these issues aren't necessarily specific to SVG. So the SVG syntax is quite verbose, and mesh structures often require many control points. And some features, such as sharp edges, can require many subdivisions. So because of this, mesh gradients can be difficult to animate. So the format used in SVG doesn't give you explicit control over the slope of the gradient. You need tensor product patch mesh gradients for that. But neither tensor product patch or Coons patch mesh gradients allow you for the smooth transitions across boundaries. So this means that there's not a one-to-one mapping between the tools like Adobe Illustrator and Corel Draw and the SVG format. So the tools have to approximate the result by generating a lot of extra patches. So these issues are sort of largely problems of authoring and control. And a lot of those issues are solved with diffusion curves, with some new issues brought to the table. So the output is similar in terms of image output, but I think the higher level sort of representation in an artistic sense for diffusion curves is really nice. So now I'm going to take you on a journey through the timeline of diffusion curves research. So the paper that introduced diffusion curves is called Diffusion Curves, a Vector Representation for Smooth Shaded Images, and that was presented at SIGGRAPH in 2008. So since then, there's been a lot of interest in the area, and the published papers typically have a few goals. So they either try to improve authoring control and add new capabilities to the model, or they try to improve the quality of the output, or they try to improve the rendering performance. And some do achieve more than one. So here I've classified the various papers into 3 groups. So the type of interpolation typically affects how much control an author has. So early papers focused on harmonic interpolation, and later methods use biharmonic interpolation, and that allows for sort of smooth transitions through curves and control of the gradient. So intermediate representations are quite a new thing as well, and they're a big step forward for performance because they allow simple transformations to be applied to the diffusion curve image without needing to resolve the equations. So let's have a look at some of the key papers. So the first paper I'm going to talk about isn't actually a diffusion curves paper, but I think it's kind of interesting to see where the original influence came from. So James Elder works in the field of computer vision, or computer, and this paper addresses the question of whether edges are a suitable representation for encoding an image. And indeed, Elder shows that image-based representation with a blur factor to show the magnitude of the intensity change can provide a high-quality representation. And then to prove that, they go and generate images from their edge blur representation. And so you'll soon see that that's very similar to the original diffusion curves representation. So this is the paper that started it all. You may have already seen these images. So this is the basic diffusion curve that I described earlier. But they also have a blur parameter, and that enables a smooth transition across the curves. So this excerpt from the paper shows how the blur is applied as a post-processing step. So the sharp color image generated by calculating the diffusion for the color channels is then merged with a blur map, which is created by diffusing the blur values. So this paper was revolutionary, and it introduced a new vector graphics primitive, but there are some limitations. So the blur method that they use for smooth transitions across curves doesn't honour artist-specified colours. So this is just a side effect of averaging the values. The curve will never hit the peak, which is the intensity value selected by the artist. Jeschke, in a later paper, showed that the method of solving is not stable under translation. So what that means is that the colour value of the pixels in the final image can change depending on how the curves are fit to the pixel grid. And Jeschke also showed that there's some colour bleed associated with small features. So a year or so later, in 2009, this paper was published. So the aim of this paper was to improve the quality and the performance of the rendering for the diffusion curves model already proposed by Orzan. And they succeeded quite well in this. So their solving method uses an iterative approach that starts with a first guess, and then over many iterations it converges to a final result. And so the initial guess for each pixel is based on the distance to the closest curve. So it can take many hundreds of iterations to reach the converged result. However, after sort of relatively few, maybe 10, the result is visually very similar to the converged result, and so you don't need to continue. And stopping early does actually have some advantages. So their solution is stable under translation, and so the result can be animated without flicker, and they improve performance on the previous method. They still apply a blur though, so there are problems with colour accuracy, but they do use an alternative technique that's much faster. And they implement their method on the GPU, and that gives them, I think, sort of a 6 to 10 times speed up over the previous method. So I mentioned that stopping the iterations early has some advantages. So basically, in doing so, that's how they make the result stable. So the constraints must be fit to a pixel grid, and in the final converged result, this is always going to give some instability, but their initial guess is based on the distance between the pixel and the nearest curve, and this produces a very stable result. So essentially, for each iteration, they're moving from the most stable result to the least stable. So the final ratio depends on where you stop doing your iterations. So the claim that the result is stable is true, but you can introduce instability with too many iterations.
Question.
Yes?
Just conceptually, I get the impression that sort of the primary focus or motivation for diffusion curves is for image processing. Is that correct?
Not necessarily, no. It's a good artistic tool. It's a good artistic tool as well. So I think there's two aspects to it, and they were both addressed in the original paper. So there's the image vectorization, which does work very well. It's a really good way of representing sort of the gradients and things like that you get in a natural image. But I think it was originally motivated by trying to create a drawing primitive that's similar to painting or sketching, or the traditional artistic methods. So it sort of addresses both.
Question, if I may. It seems like this is sort of the SVG perspective coming toward the sorts of things you can do with WebGL, 3JS, and so forth. Are there things you can do with diffusion curves that are easier than using tools such as 3JS and Babylon.js and so forth? Or and vice versa?
I don't know those libraries well, so I don't know if I could answer that. But maybe you can explain them to me later and we can have a longer conversation. So the rendering, so this is another new paper. So rendering was improving with the previous papers, but this paper is more about artistic control. So this paper addresses some of the efficiency issues that you face when authoring a Diffusion Curves image. So they suggested a few improvements, and the first of that is to control the diffusion strength. So I don't know if you can see in the far image of the bed, the shadow under the bed. So by selecting a weaker strength, you can influence how far out the colour will diffuse, or make it drop off more quickly. And so they also add a barrier curve, and this is really handy because one of the biggest pains in authoring diffusion curve images is making all the color constraints. So the barrier curve basically blocks diffusion across it without diffusing any color outwards itself, but one side can have constraints. So in the example here, if you look at the highlighted red curve in the middle image, on the left-hand side you've got solid brown, but on the right-hand side you can't just assign one color because it's abutting against many different segments. So you need to assign all these extra color constraints to get the right result. But if you have a barrier curve, you can assign the color on the left as you want, but then you can just say that the right-hand side just blocks the color and has no other influence on the image. So it's a nice time saver. They also introduced directional diffusion. So normally colors diffuse outwards linearly, but with directional diffusion, you can sort of steer the diffusion by defining a direction control. So a direction curve is just like a diffusion curve, except the result of diffusing is a vector field rather than color field. So that's kind of demonstrated here on the soccer ball. Another good addition that they come up with is these connected regions. So they're a convenient tool, and they're particularly useful in the absence of layering because they allow a color to diffuse from one closed region off into another sort of virtually connected closed region. So the example here, the wall, has a gradient on it, and that fills the area above and below the curtain rail without any extra color constraints needing to be set. So you might recognize the name on this paper. So Jasper spoke before the break. He looked at the problems and the causes of the quality problems that previous papers were having. And then to address these problems, he implemented a solver based on boundary element methods. So his result is very high quality, and it avoids many of the artifacts of the previous methods. It can't reach interactive frame rates, but there are suggestions on how you might achieve that. And this paper also has a very sort of detailed summary of the maths of the prior methods, so it's quite a good read as a starting point. So this paper's got some good wow factor. So it's mostly concerned with, this one is mostly concerned with getting good results when vectorizing or tracing an existing image. So they define a method for grabbing colors, color constraints from a source image, which had been done before, but they improve upon that method. But the really cool thing that they do is their procedural diffusion texturing. So there's a problem when you create curves and assign colors from source images that have a lot of texture because you need a lot of detail to represent that. But what they essentially show is that you can diffuse values other than color, and so they actually diffuse the parameters of the noise. So they use something called Gabor noise, and so that results in a texture that's resolution independent, and it's also got a compact representation. So it's pretty cool, and they also have a guess at the noise, make automatic guess at what the noise parameters would be. So I don't know exactly how successful that is and how much tuning they would need on top of that. But there is an iPhone app called iGabor if you're interested in playing around with what Gabor noise is. And so in 2011, Microsoft Research came to the party. So they've got a method that makes use of thin plate splines, and so this is a biharmonic function. And what this means for the author is that they can control the gradient across the curve to give a smooth transition of color from one side to the other. So the regions then become connected, and the curve no longer partitions the space into two. So previously, to achieve a similar effect, blur was used to simply mix the colors from the independent regions. They also introduced a new method for setting colors. So the colors can be specified at a point, which they call a point value. And this allows for the coloring to be specified with very few parameters. So on the right-hand side, I don't know if you can see the small color points, but they've only got about five set for that image. So they've still got curves though, but the curves are simply barriers, so they just block the diffusion from crossing them. And in their method, they call that a tear curve, and they actually define a whole bunch of new curve types. So each of these curve types adds one constraint to the image, whether it's gradient or color, and you can combine more than one curve if you need more than one constraint. So a value curve simply applies a color. A tear curve separates the two sides of the curve so they become disconnected regions. So if you combine a value and a tear curve, you get the traditional diffusion curve. And the others, the crease or the slope and the contour, control the gradient of the color transmission at the curve. So the power comes when you do combine curves. So there's many combinations possible. So I already mentioned that tear curves can be combined to create the traditional diffusion curve. So basically you have a value curve on the left, another value curve on the right, with a tear in between them. And combined curves can be offset from one another. So a value tear can simulate stroking. So unfortunately, rendering performance isn't that great for them. They use a coarse solver to provide interactive frame rates, but the quality isn't very good. So at this point, in diffusion curve authoring has come a long way, but the quality is not, the performance isn't that good. So they're not that practical yet. But in 2012, so INRIA released this paper. So this describes a vectorial solver, and it should be able to offer good rendering performance. So the vectorial solver is the solver that solves to a triangle mesh representation. And so what this does is turn the rendering process into a two-step operation. So initially, generating the mesh is still relatively expensive, but then once it's generated, the vectorial representation is very fast to render. It's scalable and it can have various transformations applied to it without requiring regeneration. So this solver also supports many of the additional authoring controls of the previous papers. So they use biharmonic interpolation, so smooth transitions across curves are possible. And they separate the control of the gradient and the color for each curve. So instead of using curve types and compound curves, as in Finch's paper, this paper generalizes the model to allow you to specify those separately or not at all. And so this is the result of the generalized model. So you've got color values along the top, gradient values down the left, and a cross means that they're not specified. So the colored cells, the highlighted ones, are the curve types from the previous papers. So you've got like a diffusion curve, a barrier curve with one value specified, a tear curve, and the various others. So the rendering performance brought about by this paper are pretty important. So the maths for diffusion curves is pretty complex, so it's always going to be quite an expensive operation. But being able to transform and reuse the intermediate representation makes them a lot more useful. And also the generalization of the authoring controls is really nice too. And this one's pretty neat. This is kind of an extension that they mention in their paper. So it's a method of applying the vectorial representation to a 3D object that results in a fully scalable vector texture. So essentially, they calculate a new mesh for the 3D object by overlaying the unwrapped mesh on top of the vectorial mesh, and then they merge them. And so this would work for sort of any triangle mesh. And it was also proposed in another paper in the same year. So that pretty much brings us to the present as far as the state of the art goes. So I already mentioned that my colleague Peter Ilbery is presenting at SIGGRAPH. So I don't want to talk too much about his paper because it's sort of his baby to bring to the world. But briefly, it describes sort of an intermediate representation and uses biharmonic diffusion. And there is a pre-press version available, so you can grab that from Cyril's website if you're interested in having a look. Got it? Cool. So how about actually using diffusion curves on the web and elsewhere? So I'm quite interested in bringing diffusion curves to SVG in some form, but there's no point if the results aren't going to be good. So there's three important prerequisites that need to be met. So the quality, we need consistent output without any artifacts or blemishes. Stability of animation, so The rendering mustn't change when rendered at different locations or with other transforms applied. So early methods, as I described, weren't that stable, but the newer methods appear to be. I mean, a vectorial representation should be stable, but we'll need to investigate that. So, and the third one is speed. So you need to be able to render it quickly. So, and after that, we look at what features you can support that are general and compatible with a range of rendering methods. So we've seen that performance has come a long way. So intermediate methods allow for extremely fast rendering support in some situations, but when the intermediate representation needs to be generated for every time, then performance isn't sufficient. But I don't think this discounts diffusion curves, but it does have an effect on what attributes are animatable. So we can consider some scenarios. So if you're using a diffusion curve image within SVG as a static image, performance should be pretty good. So there'll be some cost to generate the intermediate representation initially, but then redrawing that, zooming, scrolling, etc. will be very fast. So you could also animate the transformation applied to the image. That would be okay, as it doesn't require regeneration of the intermediate representation. So the performance for that would be the same as for a static image. But if you want to animate the curve shape data, or the colors or the gradient, then that's going to result in regeneration of the intermediate representation. And so performance for that is probably not going to be sufficient, especially in a browser where you have a lot of other things going on. But as important as quality, stability, and speed are, more important is giving artists the features needed to make beautiful images efficiently and painlessly. So the diffusion curves model, as I already said, is driven by the traditional method of drawing, where an artist sketches outlines and then fills in the colour. And even with clunky tools, artists are doing quite well. And there's also the option of vectorizing natural images. So what features are important to give artists a good experience? So, well, these come from me, and I'm not an artist, so I'd be interested if anyone has any other thoughts. But for me, the biggest pain point, as I said, is assigning all the color constraints. So anything to minimize that is good. So allowing colors to only be set on one side of the curve with the other side simply blocking is very useful. Layering also helps in a similar way, as you can bring many small parts together to create an image without worrying so much about the interaction of the curves. Biharmonic interpolation to allow for the smooth transitions through the curves is probably essential. And luckily that's supported by all of the recent methods. So you could diffuse transparency as well, because that's just another channel. And particularly in SVG, I think you want to be able to reference curves, because it seems like it would be a common use case to want to draw the stroked curves on top of the diffusion image. So if you're kind of feeling a bit inspired and interested, there's a bunch of tools that you can use to have a play with diffusion curves. They're not supported in Illustrator or CorelDRAW or anything like that, as I said, but there are some prototype implementations. A lot of it's not for commercial use, so I can't try it out myself, but hopefully you can. So it seems to me that the time is right to start thinking about how to integrate diffusion curves into SVG. Because bearing in mind that's probably going to take a couple of years. So if the working group's happy for me to take this upon myself, I'll hopefully be starting next year. So to me there's a really strong case for diffusion curves being added to SVG. So they are scalable vector graphics after all. But beyond that, the representation is extremely well suited to keyframe animation. And I've got an example in a minute. And so it's a sparse and it's a compact representation. So I don't know if everyone hand edits SVG as much as I do, but it's still nice to keep the SVG source readable and beautiful. And not specific to SVG, but I do think it is like a really nice way to author images. So I'm not an artist, and I've had fairly good results, so I'd love to see what someone with some actual talent could do. So mesh gradients, which I mentioned earlier, what about them? So they're already planned for inclusion in SVG2. And I don't think we should replace them with diffusion curves. So diffusion curves are a higher level representation from an authoring point of view, but sometimes you want to work at the lower level. So it might just suit your style, but you might need the rendering performance. And with vectorial representations as well, you could possibly make use of the existing gradient mesh rendering pipelines to render your diffusion curves. So here's just sort of an example. Don't take this as anything like what the SVG would really look like, but it's just for fun. And the result. And that's it from me, so I'll leave you with that. I'd like to thank you a lot for listening, and if you have any feedback or ideas, please get in contact with me. Cheers. Any questions? Yes.
When you're talking about putting opacity into one of those, could you have an opacity curve that would be, in some sense, orthogonal to the chromatic curve?
Yes. Yeah, I think you could. So if you looked at like the generalized model that I showed, you can actually specify curves without colors. So basically that's just a different channel that will get rendered. So I don't think that should be a problem. Yo.
Can you tweak your slide rate later?
Yes. I'm not sure where I'll make them available, but I will make them available, and I'll do that. Yep. Cool. Well, thanks everyone. Enjoy the rest of the conference.